I'm Larry Mayer. I'm the director of the School of Marine Science and Ocean Engineering at the University of New Hampshire, and I'll be talking about firsthand experience with the changes in sea ice that have been taking place over the last 10, 20 years. I'm going to try to talk about these remarkable changes in Arctic sea ice. We've heard something about it, but I'm going to give you some, hopefully, first-hand experience in terms of being there. Steve said and I spent many hours, it's actually many, many years, about 9 years in the Arctic. But I have to say, I'm not an expert in sea ice. I'm actually a geophysicist, and my expertise is in, that's sounding much better. I can speak up, I think. My expertise is in seafloor mapping and developing techniques for mapping the seafloor and visualizing the seafloor. But in that role, I've spent lots and lots of time on icebreakers with fancy mapping systems. And again, I've had this firsthand experience in watching that change of ice. I should have described what you were seeing here. You're seeing the ice cover at its minimum, which is in September in 1979 versus 2012. And we'll talk all about that and how it got there in terms of the processes that led to that. We've been mapping through almost all of that, well, not all of that time, since about 2003, almost every year. So we've seen firsthand those changes, and that's what I'll try to give you some exposure to. But first, let's talk a little about sea ice and what it is. It's basically just frozen seawater, and because it's seawater, it doesn't freeze at zero, it freezes at about -8 degrees C. And when it first freezes, it forms these tiny little crystals, about 3 to 4 millimeters in size. They're called frazzle, and what they do is they start floating to the surface, these little crystals, and when they do that, they are freshwater, they exude salt. So brine is formed as sea ice is formed, and that has a real significant influence on the density of the water and global circulation, which is driven by changes in density. So the process of forming sea ice helps drive global circulation by forming dense waters in the northern areas, and we heard a little about that over the last few days too. So those little crystals rise to the surface, they start sticking together, they start forming a sheet, and depending on the weather conditions, if the sea is calm or the sea is rough, different things will happen. So if the sea is rough, we form these remarkable things called pancake ice, and some of them are really the size of pancakes, and they look like hundreds of little pancakes floating. Some of them can be many, many meters in size. I've seen pancakes that people have gotten on and walked on, and they have this rough outer edge. And if it's calm, though, instead of pancakes, we form what's called grease ice, because it looks just like grease on the surface, although this picture has a few little pancakes in there, but we see most of this grease ice. And that starts accumulating together. And then as more and more of it comes together, it starts ridging and rafting, bumping into each other. The pancake ice will be rough on top, rough on bottom, the grease ice smooth on bottom, but inevitably rough on top, and we form the ice sheet, basically. And so there we are. It goes through a big cycle, through a season, obviously growing in the winter when it's cold, and melting sometimes in the summer. And that's really the issue, is what happens in the summer in terms of melt. So if we look at a typical cycle going from January to December, we see on average over the last 30, 40 years about 15 million square kilometers of ice at the maximum, and the maximum is about the middle of March in terms of the ice growth, all the effects of winter before the melt starts, and then coming down to about 6 million square kilometers in the summer. And that's kind of a typical annual cycle, the minimum typically being something like the 15th of September, plus or minus a few days. Looking at it from a satellite type image, we see again, I think this is 2011, which was a kind of average year. At the minimum extent, this is now in March, the maximum extent at its 15 million square kilometers, the boundaries of where the ice goes outside the Bering Sea, way down here, southern Alaska, and at its minimum, a region something like that, the 6 million square kilometers in September. Each winter that ice grows, we call that ice first-year ice. It's typically from about 30 centimeters to 120 centimeters thick. If we look at it in cross-section and as an icebreaker breaks it, it looks something like that, kind of on that size. Fairly easy for an icebreaker to get through. That will either melt during the summer, depending on how warm that summer is, or it may stay over the summer. And if it stays over the summer, we start building up what's called multi-year ice. That's ice that has survived one melt season or more. And this can be typically 2 to 4 meters thick. And this creates problems for the icebreakers. This also ridges, and some of those ridges can get up to 10 to 20 meters thick. And no icebreaker can really break through that. And I've been stuck a number of times where you sit and you back and ram for days sometimes trying to get through a ridge. It's very noisy. Now, at the end, I don't know, we'll see if we have the sound. We'll have a little video of breaking some ice. And here's what some of that multi-year ice looks like. It's several meters thick. That's probably 3 meters thick right there. That's a really beautiful blue ice as it gets compressed. And that's what really makes up the permanent ice pack, is that multi-year ice. The first-year ice comes and goes each year, but it's the multi-year ice that makes up the permanent ice pack that stays throughout the year. Well, why do we care? What do we care about sea ice? And we've heard over the last couple of days, we've heard lots of reasons about why we should care about sea ice, but probably the single most important reason is that the sea ice controls the temperature at the high latitudes, the northern latitudes in particular, and it's the thermal gradients in the Earth, the differences in temperature between the high latitudes and the low latitudes that drive the ocean circulation and drive the atmospheric circulation. That's what drives climate, is those temperature differences. And if we remove that sea ice on top, we greatly change the thermal gradients and have tremendous effect on the atmospheric and ocean circulation. And that's what all the IPCC people are looking at with great concern. So the changes in the sea ice can change the extent of what we call the thermal blanket. Just think about a very, very cold winter. The water is -1, -2 degrees, but if we have an ice cap on it, it kind of protects that relatively warm water from heating up the atmosphere, and vice versa, the cold atmosphere from cooling down the water. So it has a thermal blanket. If you remove that, you greatly change, very rapidly change what's going on in temperature. And also, as I mentioned, as you form sea ice, you're exuding this brine, and so you change the production of dense saline water, which in itself has a real effect on global circulation. Thermal haline circulation. Circulation is driven by temperature and salinity, the density differences. But probably the biggest effect of the sea ice is the change in albedo, the amount of light reflected back from the Earth. And so if we have a nice white, bright ice cap on the top, the energy from the sun come down, about 85% of that is reflected back up into the atmosphere. If we remove that ice cap, about 93% of that energy is absorbed by the water. So removing the ice cap has a tremendous effect on rapidly warming the water, and that then helps melt more ice. And we call that a positive feedback loop. And this is one of the most frightening things, and this is probably what we're seeing starting to happen, that as we start melting more ice, we generate more warming, it melts more ice, we generate more warming, and it gets faster and faster and faster. Other effects, and many of my colleagues who go to sea are stopping to go out to the Arctic because as the ice diminishes, the sea gets rough. When the ice is out there, it's very hard to break the ice, but you never get seasick because there's no motion. The ice suppresses all the motion of the ocean. And it dampens the winds, dampens the waves, but as we remove ice, we get many, many more wind, much more wind, many, many more waves, and we have a tremendous amount of coastal erosion. This is a town in Alaska that has already been abandoned because of undercutting. There are several of them on the North Shore and on islands in the Arctic that are now totally being undercut because of the great increase in coastal erosion. The melting ice also affects the ecosystem and the habitat. It now allows sunlight to shine in the water, increases nutrient production, causes changes in the rate of photosynthesis, and I think Steve will touch on that because he knows much more about that than I do. And of course, it's an important habitat itself, the ice itself, for seals, polar bears, and other kinds of animals. And we've all seen these very, very sad pictures of polar bears who need the ice, depend on the ice for their feeding, who are getting stranded, basically, because of the lack of sea ice. There's another side to it. Historically, the Arctic has been inaccessible because of the ice. But as the ice diminishes, it now allows access to the Arctic. It allows us to get up there and map. and do research, understand the Arctic in ways we've never been able to understand it before because we couldn't just get there. It allows us to have access to resources. The USGS has estimated that 30% of the undiscovered oil and gas resources are in the Arctic. This is kind of a two-edged sword that may be good for economies, not so good for the environment, and access potentially to an unknown fishery that might be in the Arctic too. One of the clear advantages of a diminished ice is the fact that it can create much, much more efficient shipping routes. If you want to ship from Europe to San Francisco or from Europe to Asia, by going over the pole, basically, through either the Northeast Passage or the Northern Sea Route on off the coast of Russia, the Northwest Passage through the Canadian archipelago, or eventually right over the top, will save you at least 40% of time, and that's huge savings, millions and millions of dollars in savings in shipping costs. So a lot of shipping companies already, last year, there were a number of vessels transiting through the Northern Sea Route. It's gone up from 1 or 2 a year to now something like 60 or 70. Well, how do we measure the extent of sea ice? How many Vikings do we have here? There were some Scandinavians here. We have a few Vikings here. Well, the Vikings have been good. They've been keeping records of ice extent along the coast for hundreds and hundreds of years, and so there's some record of years of lots of ice and little ice. They've been shipping records from the mid-1700s, saying years of heavy ice and years of less heavy ice. Russian ice charts since the 1930s. Other countries started to make ice charts in the 1950s. But the way we really know, and the real science really came with the introduction of satellites in 1979, in particular microwave radiometers. Once that, basically any object that has any kind of warmth exudes electromagnetic waves, puts off electromagnetic waves. The frequency of those waves will change as a function of the temperature. And so you can have a passive sensor that senses, in this case, microwave energy that will tell if it's water or ice because of the temperature difference. And the wonderful thing about microwaves, the reason they use that band of the spectrum, is it goes right through clouds. So there's lots of clouds always in the Arctic, but the microwave radars can see right through that. And so since 1979, we've had a series of microwave radars getting better and better, higher resolution, that have been giving us images of the ice coverage. If we put together a lot of that historical information and the modern satellite information, we see that, at least as far as the record can put together, the real changes we're seeing really started sometime here in the late 1950s. And here's where we see this remarkable decrease in the ice extent. Looking at what these radar images, microwave radiometer images look like, I'll just flip through a bunch of years. 2006, this is going to be the time of the minimum extent. 2007, 2008, 2009, 2010, 11, 12, and so on, 2013. So we get that beautiful picture from which graphs like this, and this is the kind of things you see in the IPCC all the time, that look, in this case, at the maximum ice extent from 1979 to 2014, based on those satellite images. And what we've seen is from here, from a maximum extent starting at about 16.5 million square kilometers, declining by 2014 to about 15, a steady trend, even though there's variations, and we've seen this in almost every climate-induced record we've seen, that there's always going to be variations, but a clear, steady decline, this case of about 2.5% per decade. This is of the March maximum extent of ice. If we look at the other side of that, the summer side, the minimum extent, we see even a more scary picture. Here we're going from about 8 to 5 or so here on the average line, a decline of 13% in the minimum extent of ice per decade. Again, with lots of fluctuation, just like the difference between weather and climate. Weather's changing daily, weekly. The climate has a trend, a long-term trend. Here we're seeing 13% per decade. It doesn't take very long at that kind of trend to get down to 0 extent in the summer. It's not just the extent of ice, though, that's changing. It's also the thickness of ice. I talked about the permanent ice pack being that multi-year ice. And if we look, and we heard from our folks from ESSA about some of the techniques to try to measure ice thickness. They do it with electromagnetic sensors on the ice too. They drill sometimes to do it. If we look at the change in multi-year ice between, in this case, 1990 and 2010, that's when they started to get instruments that could distinguish the type of ice. We see a remarkable decline in the amount of multi-year ice. If we look at the ice thickness on average, we see again a tremendous decline from the 80s to now in terms of the thickness. So the extent is changing, but even more drastically, the volume of ice is changing. And a way to look at it is this, that in 1983, if we looked at the distribution of ice, we'd see we'd have 1.5 million square kilometers of 5-year-old ice, very, very thick ice, and all this thick ice with this amount of first-year ice. But by 2012, we have almost no very, very thick ice left, and almost all first-year ice. So that's the really scary thing, that the extent is one thing, but the volume and the thickness of ice is drastically changing. What's the future hold? You've heard a lot over the last few days about the IPCC predictions, about the scenarios. If I go back to IPCC 4, the climate deniers are always criticizing that the climate modelers are always preaching doom and gloom. Here's a case where even the worst scenario, the bottom line here, of all the scenarios in the IPCC 4, was much better than what we actually observed in sea ice. The sea ice, the real observations, were much worse than any of the models predicted. Well, the model is learned. Modeling isn't a perfect path. They learn, and so in IPCC 5, what they've done now is adjusted the models. They've learned from the observations, and we look here at the observed data, and if we come down here, remember our different models in terms of scenarios, and the business as usual scenario, the RCP 8.5, well, that's the one that fits, obviously, the data, and if we follow that trend here into the future, it says that by 2050 or so, we're at a state of the Arctic in the summer that's called ice-free. That doesn't mean there's no ice up there. It means there's less than 1 million square kilometers of ice in the summer. Every winter, I guarantee the ice will come back. Don't go home and tell everybody we don't need icebreakers anymore. We need icebreakers, but in the summer extent, certainly the ice will diminish. So that's a little primer on ice. What was I doing up there? I've been going up there because of a remarkable document called the Law of the Sea Treaty. It's a constitution for the ocean. It's really quite amazing. It covers almost all aspects of the ocean and law. And in it, there's one article, a little article, just 617 words, called Article 76, that goes ahead and redefines in legal terms the meaning of the continental shelf. Now, to geologists and geophysicists like me, we know what the continental shelf is. It's that flat part of the coast as you move off the beach. But the lawyers went ahead and redefined it in legal terms, and they basically created a mechanism for a coastal state to extend its sovereign rights over the resources of the seafloor and the subsurface. It was really all about oil and gas, well beyond what every coastal state is entitled to, which is 200 nautical miles, if certain physical characteristics of the margin are met. And so it basically says that you have to demonstrate that this area beyond 200 nautical miles is a natural prolongation of the continental landmass. And then it gives you some very complicated formula to determine how far you can go based on the depth and the shape of the seafloor, particularly something called the foot of the slope, where the seafloor changes a gradient, the thickness of the sediments, and distances from the beach, basically. So the bottom line is that to do this, and every nation wants to do this if they can, you need to map the seafloor. Well, if we look to the US Arctic, here's Barrow, Alaska, the northernmost town in the US. Not much of a town, really, but that's where it is. So this is Alaska here, the Bering Straits. The US has what's clearly this natural prolongation, this thing called the Chukchi Plateau. So the US, even though it's not a signatory to the Law of the Sea Treaty, which is a pathetic situation, it does follow the rules of the Law of the Sea Treaty. It treats it as what's called international customary law. So we follow the rules, and in following the rules, we want to establish where the limits of our legal continental shelf are. So we've gone ahead and started a map here to find out just where we would put those limits to the continental shelf. And so we've had 8 expeditions to do this. How do we go ahead and map? Well, people have been mapping the ocean for a very, very long time. This is a statue from a tomb, an Egyptian tomb, 2000 BC. And here's this little Egyptian seafloor mapper. And what he has in his hand is a hunk of lead at the end of a rope. And so that's the way people have always measured how deep it is. You put this lead down, see how long the rope is. When you hit the bottom, you know how deep it is. Well, the next picture I was able to find is something like, I think 3,400 years later. It's a wood carving from the Thames River, and they're mapping the seafloor again. And what are they using? The exact same thing, a hunk of lead at the end of a rope. So that's how we map the seafloor for 3,500 years or so. If I jump 500 years ahead and we look at the technology, 1940, what are they doing? Exact same thing. Hunk of lead at the end of a rope. It's a lead line, it's called. And in shallow water, it's very accurate, but you can imagine in 3,000, 4,000, 5,000 meters of water, it's not going to be very accurate, and it's going to take a very, very long time. Magellan tried this in the middle of the Pacific, and he just ran out of rope. And so he called the Pacific unfathomable, and deeper, it was deeper than he could measure. About the time of the Second World War, echo sounders were developed, and what was developed was something called the single beam echo sounder, and it sends sound out. You listen for it to come back, just like listening to an echo, and if you know how fast sound travels in the water, you divide by 2 and you can figure out how deep it is. So a very simple way to measure the bottom, obviously much faster than a lead line, and maybe or maybe not more accurate, because this single beam echo sounder, what it does is it spreads out like a big cone of light would. Well, I can demonstrate it, I think. Here, I'll take my little flashlight here. It's a little point of light here. Can everybody see up top there? Or there? There. So a little bit of light here, a point, makes a big, big circle on the wall. Well, the same thing with sound. With the single beam echo sounder, the little beam of sound goes and spreads to an area that's something like the water depth. So if you're in 3,000 meters of water, that circle on the bottom that it's getting an echo from is 3,000 meters in diameter. And you only get one depth back, and you just have to assume it's directly below the vessel. So this, it kind of looks like this. And if you have something big and high up here, it'll be the depth that's recorded, but it'll be put here. So it's kind of a blurry picture of the depth of the seafloor, but certainly much better than the lead line. And from the combination of lead lines and single beam echo sounders, a single beam echo sounder gives you this kind of profile, two-dimensional profile. People put together the maps, the charts we see for the most part of the seafloor. About 25 years ago, a new technique was developed. It's called a multi-beam sonar, and instead of putting out one of these, a big cone of light, it uses lots of fancy electronics and signal processing to make basically lots of little laser beams of sound. So now the footprint on the seafloor looks like that instead of that big cone, but not just one, it puts out hundreds of those across a wide swath all at once. So we get each one of these little yellow dots is an individual, very accurate depth measurement. And this radically changed the way we look at the seafloor. 2000, that was the best map we had of what the coast of California looked like, offshore California. San Diego, where I used to go to school, Los Angeles, all these ship tracks going out, coming out of Scripps Institution, where I went there, each one with an echo sounder, and then somebody connects the dots to try to put together this contour map of what the seafloor looks like. Well, we went out for a month and a half with a multi-beam sonar and turned that picture into that picture. And that's this radical different way of looking at the seafloor. Now we get complete coverage and high accuracy. Just absolute new perspective of the seafloor in terms of all the processes and all kinds of new applications. So this is what my life is all about, is figuring out how to do this stuff. But we wanted to do this in the Arctic. So the question is, how do you do that and that stuff? And that's typical multi-year ice. That's what a ridge looks like there. And that's really hard to get through. And so we were fortunate in the US. We had a very, very big icebreaker, and we had one of these multi-beam sonars, which is several $1 million worth of sonar equipment put onto an icebreaker, but we didn't know if it was going to work, and we didn't know what was there. This was a map of the Arctic from 1570. all these bodies of land under the ice. Nobody had any idea what was under the ice, so the guess was there was these 4 bodies of land and something right in the middle. It was just total guess, I mean, somebody's imagination. We can go right to 1868. Still absolutely no idea. Nobody had ever made a measurement under the ice. But there was the prediction that Greenland continued on all the way over to Russia there. The Danes would love that if that was really the case now. They would own the entire Arctic from the Law of the Sea Treaty if that was the case. It's not. 1906, still just unknown regions. No measurements at all. And the first depth measurements in the Arctic under the ice were made by Nansen, who did this amazing drift. If you don't know the story of the Nansen Drift, it's an absolute amazing story. For 3 years, set a vessel in up here and it drifted through. Let's see, set it up here and it drifted through and finally came out. He was trying to get to the North Pole. He predicted he'd drift to the North Pole. He came very close, then saw that the vessel was going to miss, so he got off and started to walk there. He and a buddy didn't make it either, but actually was able to walk back and get picked up later. But he made 7 or 8, I think 8, each one of these little dots, 8 of these lead line measurements. And from that, drew the first map of the Arctic Ocean as a deep ocean. I don't know how he predicted the rest of it was all an ocean from that, but he was pretty close to right. After that, the Cold War came, lots of interest, Russia and the US, but the measurements were still basically individual measurements. Fly out, dig a hole in the ice, put something through, an echo sounder, a magnetometer. They also had ice islands, that big hunks of, this is continental ice, that broke off a glacier that would float around. This one for 12 years, and so you can make measurements from that. But maybe there were 60,000 individual measurements in the entire ocean by that time, till 1980 or so. But from that, a very blurry picture started to form of what the Arctic Ocean looked like, and it wasn't one basin, it was actually 2 basins, and there seemed to be a ridge in the middle. And then US nuclear submarines and British nuclear submarines came along, and they don't like to turn on echo sounders, but they would every once in a while. In the 1980s, some of that data started to be declassified. We got access to some of that data, so we started to put together a better picture, but still not a very good one. Submarines have a problem of not knowing where they are. If they don't surface, they can't see satellites, can't do GPS, and their navigation systems will drift many, many miles over months. And so most of the features that we found that the submarines have mapped are off by a few miles. So that makes it a very scary situation. But as I said, we took our big icebreaker, the Healy, put a multi-beam sonar on there, and then headed off in 2003, and so did a number of other countries. The Canadians with a smaller icebreaker, can't go into deep water, it's a shallow water multi-beam. The Swedes with the wonderful icebreaker, the Odin, which I'll be on this summer off the Russian margin with a multi-beam sonar now. The Germans with the Polarstern, and in the last 2 years, the Russians have put multi-beam sonars on too to start mapping their side. And so we're starting to now get a much, much better picture of what the Arctic looks like. But none of that probably would have been possible if we hadn't seen these changes in ice over the last 15 to 20 years. Not one of these icebreakers on its own could have gotten into any of these areas probably 30 years ago, 40 years ago. And so let's take a look in the context of now the minimum curve we said. Remember that 13% decrease? The September curve. We always tried to go up there August to September, August to October, because that's going to be the minimum ice. We don't want to break ice if we don't have to. We started in 2003, which is kind of an average year along the average line there. And we had no idea if this was going to work. If we play the video at the end, you'll see breaking ice is tremendously noisy, and with the sonar, you're sitting there trying to listen to a very quiet little sound. So was it going to work? Could you break ice and map at the same time? Our first trip was just a test trip, just 10 days, get up to, there's a negotiated boundary between the US and Russia along here, get up there and start mapping the edge of this Chukchi Plateau to see if we can do it. And what we found was first year ice, relatively easy to move through with the Healy as an icebreaker. We had planned the cruise to move at 3 miles an hour through the ice. We were actually able to go at about 6 knots, really, nautical miles an hour. So things went very, very well. And we found we were able to hear, not easily, but we were able to hear the bottom. We had to do a lot of fancy signal processing, but we were able to do it. We found things that the existing maps were really not anywhere close to being right. Found things like a 3,100 meter high seamount, right where several submarines had crossed over and said there was nothing there because they didn't know where they were. And over the years, we found many, many more of these big mountains that are not on any map in the Arctic, and I'm sure there are hundreds, if not thousands more. Based on that success, in 2004, we went back to continue mapping along the edge of the margin. That was our plan. That was going to be a 20-day trip. 2004 was not much different than 2003 in terms of the close to average ice year. But in 2004, we found ourselves stuck hard. This is where 3 days we were stuck backing and ramming, not being able to get out of the ice pack. And actually very scary, to me it was scary at least, because as I was a chief scientist, so I go to a meeting with the captain every day, and as we're doing this, he said they start talking about plan A or plan B. Plan A was that they winter over. The vessel can basically stay over the winter, and the food was terrible to begin with. I mean, you know, on a regular 20 or 30-day trip, it was terrible food. You can imagine 360 days later what it might taste like. Or they call in the Russians with a nuclear icebreaker to get them out, and they weren't about to do that, you know. So I thought we were going to stay there, and we finally got out, and they just kind of retreated down south. There's, you see the edge of the ice. But the interesting point to me was, on the average, these were the same, but on a day-to-day basis, it really depends what the local conditions are, what the local wind and what the local, what they call accommodation. To break ice, you need a place to push it. So if there's only 1% of ice in the Arctic and it happens to be around you, and the wind is pushing it around you, you're going to be stuck. So you can't just, again, have this concept of an ice-free Arctic where everybody can go in their kayak and swim around. So we retreated and started to map off here. The next year we went back was 2007, and 2007 was the remarkable year in terms of the ice minimum. Really quite different, and it was palpable, because we now got into the multi-year ice, and this is the permanent ice pack now being broke up into small pieces. And that does not heal itself in a year or two or three or four. This will take tens, if not hundreds, of cold summers to actually get that back. And they made it very easy to map, I have to say, because those big pieces could get pushed aside, but very, very bad for the Arctic. So this was really the beginning, in my mind, of the breakup of the permanent ice pack. Just some more examples. So that's, you know, it's 3 meters thick, 4 meters thick, multi-year ice, just being now broken into small pieces. It'll let us map much more. We were mapping up here, but given the ice, we were able to run way up here. Made great discoveries that the actual edge of our margin was not where we thought it was here, because our maps had been so bad before. It was actually up here. But you see also the way we map, because we're breaking ice, is just in a single line, not in this complete picture, complete coverage I showed you off the California margin. The next 4 years, again, were fairly average years. We were moving further and further north now that we found our margin was much further north. So we collaborated with the Canadians, even though we have a great battle. We'll have overlapping claims with Canada. As scientists, we cooperated, both of us realizing we both need to map there. It's a lot easier to use 2 icebreakers than one. One can break in front, and then the sonar system can get behind in the quiet water. So we had the sonar system, they had a different type of system where we would switch back and forth. Lots of collaboration, always getting stuck in the multi-year ice. And one vessel would come and break the other out. Sometimes very, very close collaboration. At this point, this vessel is moving backwards at full speed. And that's how close it comes to try to break out this vessel, which is the Canadian vessel. You can tell it's the Canadian vessel because the Canadian sailors are wearing their winter uniform with shorts. And I wanted to point out one year that was special in 2011, where we came about 80 miles from the North Pole. We went very, very far north. In that case, not for US purposes anymore, for Canadian purposes. And there we really got into heavy multi-year ice. Very difficult to maneuver, and the Canadians actually deployed an autonomous underwater vehicle to start mapping under the ice. The first time a vehicle went out under the ice, went 200 kilometers and came back. It was really very, very impressive. But the nice thing when you're in the ice like that is you can stop almost anywhere. The ship can just stop, you can get off, walk on it. It's, it's pretty amazing that however many hundreds of tons vessel this is can just stop, and right next to it you can stand. It's how thick the ice is. But even the hull plates in the bow of a vessel like this are about this thick steel, but it takes a beating going through the ice. When it does go through the ridges, it's really something. And we deploy instruments on the ice that actually try tracking the ice, so the ice modelers can both measure the thickness and see where it goes through a season. So the last year we went up was 2012, and if we thought 2007 was an amazing year, 2012 was a real shock to us. And this was by far, so far, and I've got caveat of so far, the greatest minimum in ice extent in the summer, down to less than 3.5 million square kilometers. And I tried to find a way to express how this was, and I knew that through all the years we must have been in the same place at the same time with the vessel. So I wanted to say, let's show a place to show how different it was in 2012. Let's show what it was in an earlier year. And it turns out right up here, about 80 north or so, we had been to exact spot in 2012 and in 2007, which had been the previous ice minimum year. So here was this spot in 2007, 80 degrees north, 80.5 north. And you see in 2007, that was the year I said that these are all ice ponds. There's still thick multi-year ice here, but it's really getting soft and breaking up. That's what I said that we saw the breakup of the permanent ice pack a little further south that year. The same spot in 2012 looked like that. And you can just barely see the ice edge there. And this is at more than 80 degrees north. Every year, even in 2007, we ran into the ice margin at about 75, 76 degrees north. Even 2007, that's where the margin was. It was broken up now, but it was still there. In 2012, that's where we ran into the ice margin. So something really, really changed in 2012. But it let us now map, instead of in our little, just one tracks, it now let us map way up north here in ways we can never map before. It was open water. People got seasick. That's why my colleagues don't want to come back, because it was rough. But again, once you start mapping like that, you see amazing features. This is a deep sea channel that nobody knew existed, and we still don't understand why, running at about 80 degrees north. So 2013, I didn't go back to the Arctic mapping. Well, I did, but I went to Greenland on a 51-foot sailboat with a mapping system, with a little smaller sonar system. This was to actually look at the potential for paths of warm water coming into the fjords in Greenland to see if we can explain why the ice sheet is deteriorating so fast. It was also part of a wonderful adventure on this beautiful sailboat. But 2013 was a very, very interesting year, because if we look at the ice, the minimum ice extent record, we see that that was 2012. It came back in 2013. And the climate deniers went crazy. Fox News, sea ice up 60% in 2013. Arctic, and now it's global cooling, return of the Arctic ice cap, it grows by 29% a year. Well, you see, they can't add to it. The math isn't too good. Some of them say 60%, some 29%, but it's okay. Al Gore forecasted ice-free Arctic, ice cover expands 50%. The climate deniers just went crazy. Well, the sea ice had come back, the first year ice, at its minimum extent in 2013. But look at it in the context. Look where it is. It's still the 6th lowest ice extent in record. Nothing has changed. It's just this normal fluctuation back and forth. We're still on this remarkable decline in terms of the ice extent. And so, to summarize this, the sea ice extent has been very rapidly decreasing, and all the indications are that it will continue to do so. They may have some benefits in terms of shipping, increased access, but there are many, many negative impacts, and I think Steve will expand on this a lot. We're going to see the destruction of critical habitat, increased coastal erosion, and the scariest one to me is the complex and not yet well understood impacts on atmospheric and oceanic circulation, so global climate. And this is the concept of the tipping points that many of our earlier speakers talked about. Because if there's one thing that can cause a tipping point, it's really this positive feedback loop, which just starts accelerating things. And all we need to do, and this has happened in geologic time, is turn off the global circulation, the global conveyor belt, and then we have a totally new state. And I don't think the climate modelers have yet taken into account the impact of this diminished sea ice in the climate models. They're just starting to incorporate it now to see what the feedback effects going on there are. And so my contention is that of all the scary things we've heard this week, this is perhaps the scariest. But what I really wanted you to see was, you know what that is? It's an ice bow. They exist. They're made of, it's a rainbow made of fine ice crystals. And so there's hope. In oceanography, we tend to end talks with a sunset, but the neat thing about the Arctic is you can have a sunrise and a sunset in the same picture. So that's it. That day, the sun came up and then set. And that was it. So thank you very much.